In a previous video, I mentioned when introducing trigonometry that the most that a sine and a cosine function can be equal to is 1. We know that because the sine and the cosine function, let's start with sine. Sine of theta is equal to the opposite over the hypotenuse. The hypotenuse is always the longest side of a right triangle, so the most that this can be is when the opposite side actually equals the hypotenuse, and then you have a number divided by itself. We know then that this has to be less than or equal to 1. The same is true for the cosine function. So for cosine, we know that this is the adjacent over the hypotenuse. This has to be less than or equal to 1 or 100%. But these individual values, say the opposite side and the hypotenuse, or in this case, the adjacent side with the cosine function, these can of course be any length. So when we have a vector, which we'll be working with many vectors, and we treat it like the hypotenuse of a triangle, we said that we can break this down into its components. So I would have a horizontal component, and I would have a vertical component. And now we can use trigonometry to find these various components if they're missing, if we're not given the value for each of those. We could also find the hypotenuse. Maybe we're given an angle here, theta, and one of the sides, then we could find the hypotenuse. So these values can be any number. When we're finding components, they obviously aren't restricted to 1. That's just a property of the sine and the cosine function because the most they can be is 100%. But these individual values, the hypotenuse or the opposite side, for example, could be any value. Like, for example, maybe this is a displacement vector, d, and maybe it's equal to 500 meters northeast, right? So that's a possibility. So if this is equal to 500 meters, obviously these values, these components are going to be more than 1. So then how do I find these components? So I'm going to start with the new triangle here. And the interesting thing about trigonometry, and this is just a property of our universe and a property of triangles in the geometry of our universe, is that if you know the distance to something, let's say that this is a tree. I'm going to do my best attempt of drawing a tree here. So if this is a tree, obviously if you're standing on the ground, you could measure the distance to walk towards the tree. So you could measure this horizontal distance, right? This is something I'm talking about, this distance right here. You could measure this, right? We'll call this d sub x because you would just start and you'd take a measuring tape or some other measuring device and you would walk to the bottom of the tree. There are also measuring tools that can tell you the angle. If you angle upwards and you sight in the top of this tree, you can actually measure the angle of the top of the tree with respect to the ground. So if you know those things, you might already be aware of the fact that if you have an angle and a side, then you can do some algebra to find the other values. So the thing that I'm interested in finding in this case would be dy. For this kind of problem, it might be practical to say, hey, how tall is that tree? Well, for this case, we would actually need to know dx and the angle. Like I said, we could cite this in, and then we could find dy. And now we have to ask ourselves, with our 3 common trig functions, sine, cosine, and tangent, and I'm going to write our mnemonic, which is always useful to write if we can't remember it. So we have so, ka, toa. So this mnemonic helps us remember the different properties of these respective functions. So I see that sine has the opposite over the hypotenuse. Well, unfortunately, I don't know anything about this hypotenuse d at this point. The cosine tells us about the adjacent and the hypotenuse, and the tangent tells us about the opposite and the adjacent. So I have the adjacent angle. Let's say It is 100 meters. And then if I have that and the angle, I can find dy. So let's give ourselves an angle here. Let's say that this is 50 degrees. So with that information, I'm going to write the tangent function, the definition of the tangent function. The tangent of an angle is equal to the opposite over the adjacent side. And those sides are all with respect to the angle theta. So the opposite side is d sub y, and the adjacent side we said is dx, so that is 100 meters. Now this is a triple equality here, which is perfectly fine. You can continue writing as many equations as you want as long as everything is equal. So we know then that everything on these three sections has to be equal, so the tangent equals this far right side. So I'm going to rewrite that just so it's a little bit clearer. So that's the tangent of theta now we're saying is equal to dy over 100 meters. Well, this is just a simple equation. So if it's not perfectly clear, remember that tangent theta is just tangent theta over 1. So this is two fractions, and basically we cross multiply. So I'm going to multiply 100 on both sides, and that becomes then 100 times the tangent of theta equals dy. And the last step then, we said that theta equals 50 degrees, so this then becomes 100 times the tangent of 50 degrees equals dy. And that's our answer. Now, if we want to find the numeric form, we get out our calculator, and we want to be sure this problem that we are solving is in degrees. So we want to be sure that we're in degrees and not radian mode on our calculator. And we just put in 100 times the tangent of 50 degrees, and it's going to give us the answer of dy is equal to 119 point, I'm going to round to 2 decimal places, so 1/8, and these are meters. So that's kind of interesting. If you know the distance towards something, the horizontal distance, and an angle pointing upwards, you can actually calculate the height of something. That's much more useful than trying to climb a tree and figure out the height. And there are tools that can tell you the angle of something if you sight it in with respect to the ground. So this is actually a problem that could be performed practically in real life. So that's really useful. Okay, so I'm going to do just some more problems here. I want to be able to provide more examples and just be sure that we understand these concepts. I'll probably actually make another video that also is just working some problems with trig, because sometimes it can be a little bit tricky, and the more problems we work, the better we're going to get at it. So let's say, for example, that what we're given is a right triangle and we're given the, let's say we're given this side over here of 50 meters per second. We don't know what the adjacent side is, but we want to find the hypotenuse. This is going to be a velocity. So this is a velocity vector. This could be any quantity. I'm just deciding, hey, let's pretend that this is a velocity vector. So this side, this 50 meters per second, we're calling this Vy. And the adjacent side we're calling Vx. And let's pretend that this angle here is 30 degrees. Okay. And I want to find the magnitude of v vector. Now, why didn't I say I want to find v vector? Well, I already know the direction that it's going. It's going 30 degrees northeast. If that's not perfectly clear, let's draw our coordinate axis here. And pretend that this is horizontal. So this is y and this is x. We see we're in the first quadrant of our Cartesian coordinate system here. So this is north, east, south, and west. So just looking at this, we're in the first quadrant. This is the first quadrant, this is the second quadrant, the third quadrant, and the fourth quadrant. So we're in the first quadrant, and we can see that we're pointing 30 degrees, and we're saying 30 degrees northeast. That's 30 degrees with respect to this horizontal line. That's what that means. So we know the direction already, we just don't know the magnitude of v. And we can find that pretty easily here just using our trigonometric functions. So I have the opposite side to this triangle, and I have a degree. So going back up here to my helpful reminder here, this mnemonic, we know it's SOHCAHTOA, and I have an opposite side. I'm trying to find this hypotenuse right here. So I'm also given an angle, so it looks like we can use the sine function. So the definition of the sine function is the sine of theta equals opposite over the hypotenuse. Okay, now let's plug in what we know here. So the opposite side is Vy, V sub y, and that is 50 meters per second. And this is divided by the hypotenuse, which is, we're just going to call it v, not v vector, but v, because we're just interested in the magnitude. So the other thing we need to do now is plug in our angle. So this becomes the sine of 30 degrees equals 50 meters per second divided by v. Okay? And now I'm just going to rearrange this and multiply both sides by the magnitude of v vector. I'm multiplying both sides by v. So I'm going to multiply this side by v, I'm going to multiply this side by v, and it becomes then, the equation is v sine of 30 degrees equals 50 meters per second. And now the last thing I need is the sine of 30 degrees. We know that this is just a number. So I can divide both sides by the sine of 30 degrees because it is just a number. So I'm going to divide both sides by sine of 30 degrees. And then we're left with this equation, v equals 50 meters per second divided by the sine of 30 degrees. And I can plug that into my calculator as well, and it's 50 divided by the sine of 30 degrees. Be sure to use your parentheses if you have to in the calculator. That'll help with order of operation errors. And the result I get for this is 100, and we know the units are meters per second since this is a velocity. So v vector total is 100 meters per second at 30 degrees northeast. So that would be the vector. Remember, to make it a vector, we have to attach the direction. The direction comes from this 30 degrees, which we're already given. So that's a way to find the hypotenuse of a triangle using our trigonometric functions. I'm going to create a second video where I'm going to work some more problems. I'll use the arc sine, the inverse sine, the inverse cosine. So we can just get a lot of practice and have a lot of examples as to how to use these trig functions.